Hello, these are the solutions to the EM induction worksheet, basically using right-hand rule to determine direction of the induced EMF. So in the first question, we have a coil of wire entering a uniform region of uniform magnetic field directed out of the page. To find what happens on the coil, we have to look at the change in magnetic flux. Now, magnetic flux is magnetic field, cross-sectional area in the field, and cosine of the angle between them. In this situation, field is constant, angle is constant. It's the area exposed to the field that is changing. Basically, this much is the part that is included in the air in the magnetic field. So as it comes in, you can see that this area gets bigger and bigger and bigger. So we have increasing magnetic flux, lines that are pointing towards you out of the page. So imagine that as a magnetic field that is pointing towards you and increasing, which would mean your north pole has to point towards the paper, which means your four fingers curl in the clockwise direction. So that's that. And as it enters, this time the area is decreasing. So it's in a magnetic field towards you, but it's getting weaker. So it's like a north pole going away from you. So to attract it, your south pole should point towards it. So your south pole should point towards the going north pole, which means now your four fingers curl in the counterclockwise direction to attract the north pole going. In other words, to oppose the change. So answer would be C. Question 2 is asking for the units of magnetic flux and magnetic field strength. Magnetic flux unit is the Weber, and magnetic field strength is the B that we know, that is Tesla. So answer is B. In question number 3, we have an aluminum ring that is free to hang, and there's a bar magnet that is approaching. We don't know the polarity of these, but we know the opposition rule. So Lenz's law states that the induced current will be in a direction such that it will oppose the change. Let's say this is a north pole. There will be induced current on this coil so that its north pole is this way. So your right hand will be like that. So when a north pole is coming closer, to repel a north, your thumb point towards it, so the current will be like that, which means it will be repelling. And if it was going away, then your right hand would be placed like this, because for a north pole going away, induced current will be in such a way to attract what is going away, which means the south end of your hand will point this way, so the current will be in the opposite direction. But either way, if it is coming closer, this will be repelled. If it is going away, this will be attracted. So answer is B. Number 4. We have a bar magnet close to a coil with a south pole near, so the field lines are pointing towards the left. And there's an ammeter connected to the coil. So which of the following will the ammeter indicate a current? There is induced current when there is change in magnetic flux. So the first one, the magnet and the coil both move to the right with the same speed. This is when relatively there is no change. If they're moving with the same speed, they're not moving relative to each other. They're not getting closer or further, so there's no change through the coil in terms of the magnetic field line. So this will not cause an induced current. The magnet is stationary and the coil moves to the left. That's when there is a decrease in the magnetic flux because it's going away. So it would induce current. And the number 3, the coil is stationary and the magnet moves. Again, there is change. So 2 and 3 will cause an induced current and the ammeter will measure. Number 5. A coil and a magnet can move horizontally to the left or right at the same speed. In which of the following will a conventional current be induced in the direction shown? So you want the induced current to be towards yourself like this. So that's when, let's see what happens. That's when the south pole of your induced current would point towards the north. That is when it will be trying to attract the north. So that happens when north is going away. Likewise, if the coil is going to the right when they're moving away, it will want to attract. So answer to number 5 would be A. So when a north pole is coming closer, to oppose that, to repel the north, you place your right hand like this, and you will see that the current flows downward on the front end. So when you continue that, here on this line you have current flowing from P to Q. Number 7, you have north pole coming down. So we want to know why the magnetic flux in the ring is increasing. Because the magnetic field at the position of the ring is increasing, the magnet is getting closer. So if these are the magnetic field lines, the closer the ring is, let's say it's at that distance, you will see it will be exposed to more lines if it's closer, or less lines when it is further away. And on diagram 2, which is the top view, state the direction of the current, induced current in the ring. So if the north pole is coming closer like this, to oppose that change, it would be in the counterclockwise direction. And the last question, a metal ring is placed in a magnetic field which is directed upwards. The flux through the ring increases over a time interval, which is shown in the diagram, which with more magnetic field lines. State and explain the direction of the current induced in the ring during this change. So the field that is existing in the region is upward on the page, and it's increasing. So to oppose that change, you flip your hand to face in opposite direction to it. So the hand, your 4 fingers, will curl in a clockwise direction. This is a 3-mark question. Step 1, induced field must be downward. This is to oppose the change, and as a result you have current flowing clockwise induced in that direction, and that would give you the 3 marks. Thank you.